Hello everyone, and thank you very much for attending this lecture. My name is Francesco Tacchino, and today we will discuss about quantum models for machine learning and neural networks and their applications. So let me start by recalling what classical neural networks are. These are mathematical models which, as the name suggests, are inspired by an abstract representation of the behavior of biological neurons and neural networks. So these mathematical objects that we call neural networks are composed by a series of layers, and each layer contains a number of fundamental units that we call perceptrons or artificial neurons. Now, as you see here on the right, these perceptrons, so the fundamental units of classical neural networks, are essentially small, simple, nonlinear functions by themselves. So they accept, in particular, a number of inputs, for example, real numbers, which they combine with another set of real numbers that we generally call weights, the W's in this plot. And then they compute a nonlinear activation signal, for example, an hyperbolic tangent or a sigmoid, which in turn becomes the input for the next layer. So in general, classical neural networks end up being big functional compositions parameterized by a set of three parameters, which are essentially the weights associated to the network connections. We are in general free to adapt or to select these weights in such a way that the whole computation of the neural network represents some specific function of the inputs. Now, one of the most important characteristics of classical neural networks is that they can learn and adapt their parameters in order to compute or approximate essentially arbitrary functions. The most popular setting in which classical neural networks are used is probably that of supervised learning. So in supervised learning, you feed to the network a set of inputs and which are part of a training set and a number of associated desired outputs that you would like your neural network to compute. Now, through a suitable learning procedure, the network can adjust its weights in such a way that the output that it provides is more and more similar to the desired set of outputs. Of course, the idea is that after the training, the network will be able to generalize on previously unseen inputs. Classical neural networks are indeed very powerful models and have been used extensively for many applications in classical machine learning. So the natural question when we approach the world of quantum learning is, of course, can we build a quantum version of neural network models, for example, to achieve speedups over classical counterparts or to develop new applications? Well, if you have a quick look at the literature, you will find that the answer is essentially yes, at least to some extent. In fact, you will find a lot of models around which are called quantum neural networks and are at least inspired by the structure or the functionalities of classical neural networks. Now, today we will only see a limited set of these possible quantizations of the classical network idea, and I strongly encourage already from now you to go in the literature and have a look to all of the possible flavors and applications that are available. The starting point will be quantum perceptron models, which are the analog of the single nodes that compose neural networks. We will see how these building blocks can be used to scale to develop more advanced applications like quantum convolutional neural networks or dissipative quantum neural networks. If you're interested in this paper that you find here at the bottom of the slide, you will find a summary of some of the topics that we will discuss today. And most importantly, you will find the references to all the original works that we will review in the rest of the lecture. So when people started to think about the possibility of developing quantum versions of classical neural networks, the natural place to start was, of course, the fundamental units of the classical neural network model of computation, namely perceptrons. So from the very beginning, we immediately realized that there is a very characteristic feature, actually the defining feature of classical perceptrons, which is not immediately easy to implement in a quantum model. And this is essentially the nonlinear behavior. Indeed, as you know very well, quantum computation and quantum mechanics in general are linear from the mathematical point of view, so that the typical transformations that one can realize on quantum states are, for example, unitary operations which are linear in the inputs they receive. As a result, special attention must be devoted in the way classical information is encoded and manipulated by the quantum algorithm in order to obtain effectively the nonlinear behavior that you typically associate to classical perceptrons. Now, a number of different quantum perceptron realizations have been proposed over the years. As an example, in this case, for example, the well-known quantum Fourier transform algorithm was taken as a step towards the calculation of the activation behavior of the perceptron. Other cases, for example, use repeat until success schemes to achieve the nonlinearity. And in other instances, essentially the only natively nonlinear quantum operation that you can have, namely quantum measurement or wave function collapses, was used to determine the activation state of the neurons. Now, what is common to many of these applications and models, and that will later make quantum perceptron the basis, for example, of dissipative quantum neural networks, is that the perceptron in the quantum mechanical language is essentially a controlled unitary operation. So this is what I essentially mean with this box here. In a way, the set of the inputs is now represented by a register of qubits having the role of controls, and these qubits control parametrically a unitary operation on another register, which is the one that we can take as the output of the neuron. Now, these outputs can be classical outputs, for example, if we measure an activation state as a real number from the neuron, but can also be quantum outputs, so manipulated quantum states that we can, for example, use to proceed in the computation. There are, of course, many easy tasks that you can perform with single nodes, even so, for example, think of what you can do with a classical perceptron, and we will see an example in the second part of this lecture. Of course, however, the full computational power of classical, at least, neural networks goes well beyond what one can achieve with individual nodes. And so the next step is to find a quantum model which more closely resembles the functionalities that one can achieve with classical neural networks. In particular, the main functionality that one may desire is the ability of systematically approximating large classes of functions. Now, let's get back to the original setting of classical neural networks that I described at the beginning of the lecture. And you may recall that this is a layered structure, and layers are the ingredients that we will port to the quantum case. So, as you see, in the classical setup, information flows from left to right in this plot. So you have an input that you give at the beginning of the computation, and the information is then processed throughout the network up until the point where we can measure an output, which again can be described as a big functional composition parameterized by a set of free parameters that we call theta. These features, namely the layered structure and the presence of trainable parameters, are also part of a very specific class of quantum algorithms, which have become more and more popular over the last few years. And these are known as parameterized quantum circuits. Now, because of this similarity, people started to call these models, sometimes a bit improperly, quantum neural networks. There are many different versions of parameterized quantum circuits that one can consider, and in this lecture we will put ourselves in a fairly general situation in which the layers of parameterized unitary operations that are present in our quantum neural network will be of two kinds. One is which is parameterized by input variables, so you see the x is the classical input, and these unitaries here depend on this classical input, and the other kind of operations will be one which depends on a set of trainable parameters, theta. You should immediately notice from this diagram an important difference with classical neural networks, namely the fact that the input can be uploaded into a quantum neural network not only at the beginning, like in the classic case, but in general at any stage of the computation. We will actually see in a moment how this impacts and has an effect on the class of functions that the quantum neural network can compute. On the other hand, the U of theta operations in the diagram play the role of trainable connection weights in classical neural networks. So these thetas can be adjusted in a feedback while training your model, for example. The output of the neural network is obtained, of the quantum neural network is obtained by measuring some generic observable on the qubits at the end of the computation. This is what I represented here with this generic operator M. So the workflow is essentially the following. You start from some reference state, for example, all your qubits initialized in state 0, and you apply a series of layers which can contain either input-like or weight-like unitaries. And then you reconstruct the classical output, for example, one or more real numbers, by a series of measurements. This output will be, of course, a function of the classical input that you give, and it will be parameterized by the set of three parameters theta. So again, the classical and quantum cases show some similarities, for example, in the fact that they have a layered structure and that they rely on trainable parameters for their adaptive learning. However, there are many differences between the two. And in particular, while in the classical case, we have a usual feed-forward scheme where the input is given at the beginning and then it's processed while it travels through the network, in the quantum case, the situation is different and the input can, or sometimes even must, be re-uploaded over and over. This design choice is actually related, as we will see, to the fact that in general, the real most important difference between classical and quantum neural networks is that the fact that the native operations that we can perform in the quantum case, so the quantum layers, are always linear unitary operations. Now, one of the most important results for classical neural networks is that they turn out to be essentially universal functional approximators. So by adjusting the parameters of a classical neural network, which is complex enough, one can in principle approximate an arbitrary function of the inputs. Interestingly, a similar result also holds for the quantum neural network model that we just introduced. Although the way this result is achieved is a little bit different and is characteristic of the quantum case. Universality for quantum neural networks was in fact discovered and discussed very recently in a number of works that I'm listing here at the bottom of the slide that you might be interested to check to find proofs and further details. So the idea is essentially the following. First of all, it can be shown that the quantum neural network model that we just defined is essentially capable of computing partial Fourier series. So the output of the quantum model that we defined is a sum of imaginary of complex exponentials with a set of frequencies which are determined by the properties of the network and which are linearly combined with a set of coefficients. A crucial result in going towards the universality of quantum neural networks is the fact that the spectrum of available frequencies is determined only by the encoding part of the circuit, namely the operations that directly receive the classical input. For example, the S of X here in these green boxes. In particular, if we call H an Hermitian matrix defining the encoding unitary S of X, which is repeated around in the circuit, the available frequencies are combinations of the eigenvalues of this H. Moreover, the size of the spectrum, so the number of available frequencies, increases with the number of times the operation is repeated. So the more times you upload the same classical input, the richer the spectrum of frequencies will be. Nothing about the frequencies can actually be changed by adjusting the trainable parameters. So crucially, in quantum neural networks, we have to repeat the encoding many times if we really want to use these models as functional approximators. Of course, the trainable unitaries do have a role, and in particular, they have the role of fixing the coefficients in the Fourier series. Now, under suitable hypothesis, the universality is granted as soon as we are able to implement arbitrary trainable unitaries and measure arbitrary observables. Let us see an example just to fix these ideas, these concepts. Now, if you take, for example, a single qubit and upload the input just one time, as in this circuit here, the output will contain essentially just a single frequency. And so the function that you will be able to compute is essentially a sine or a cosine function, like here. As a result, of course, you cannot approximate well a target function containing, for example, more than one frequency component, no matter what you do with your trainable layers. However, as soon as you increase the number of times that you upload the same input, the function that the network computes starts to become more and more complex. And for example, this is what happens if you, for example, repeat the input 3 times. And in this last case, your frequency spectrum is rich enough that you can, in fact, approximate the target function that you wanted. Let us notice two more things here. One is that when you use the same single qubit rotation to re-upload your input to the quantum network, the spectrum size grows linearly with the number of repetitions. The second thing to notice is that there are in principle two possible ways of repeating the input operations. One is doing it sequentially, like we just saw. So you have, for example, a single qubit and you alternate an encoding unitary with a trainable unitary, with an encoding unitary, and so on. And we may call this a series encoding. However, there is also a parallel encoding version in which you use more qubits and less circuit depth. Here you essentially repeat the encoding many times in parallel on the different qubits. So from the point of view of functional universalities, the two schemes are perfectly equivalent, of course, if we assume that in both cases we are able to implement arbitrary trainable unitaries. Okay, this is all I wanted to mention about an introduction, a general introduction to quantum neural networks and their properties. So what we will do now for the rest of this lecture is, first of all, to review some examples of neural network-inspired quantum models that have been proposed over the years. We will do this journey by taking one example of a popular classical model, namely convolutional neural networks, and see how this model was quantized or has inspired the new quantum models. In the last part of the lecture, we will do a sort of mini workshop, in a sense, during which I will present a simple model for classification, which of course will be a very introductory example based on some published work, but for which I will also report some results obtained on real quantum hardware. So let's go to convolutional neural networks. Convolutional neural networks are a very popular and widely used architecture in the classical world, and you probably have heard about the names of some of these models like LeNet or AlexNet. Convolutional neural networks are used in the classical world, for example, for the analysis and classification of large images. These inputs are typically too large in size to be treated with conventional, fully connected feed-forward networks. So convolutional neural networks make the task easier by alternating a series of different specialized layers called convolutional layers and pooling layers. Convolutional layers analyze local portions of the image, for example, that you want to analyze. So imagine that, for example, we want to classify a picture from a Qiskit event that we attended last year. We first convert this image into a mathematical representation in which, for example, every pixel is represented by a number, and the whole image is essentially a matrix of this kind. A convolutional layer applies one or more local filters which are shifted over small parts of the image. So you perform typically a dot product plus possibly a nonlinear activation to the combination of the pixel values and the filter values. And what you obtain with this procedure is a transformed image, or a set of transformed images if you use more than one filter, which are called convolved features. Of course, each filter can be specialized to detect specific patterns or elements in the image. Now, these transformed features then undergo dimensionality reduction in the so-called pooling layers. The convolved feature matrix is divided again into local regions, and each one of these regions is condensed, for example, into a single value, taken as, for example, the maximum or the average or the sum of the inputs. This makes the input more manageable for successive layers and makes the network resilient, for example, to small changes or scaling variant. Now you can repeat this convolution and Pulley schemes for as many times as you want in order to reach at the end a feature dimension which is much smaller than the original big image that we wanted to analyze. Now, the dimension is typically small enough that we can in fact apply now a fully connected layer which does the final classification. For example, in this case, correctly recognizing that we have a Qiskit logo in our image. The structure of classical convolutional neural networks can be adapted and is very flexible. Most importantly, you can, for example, change the number and nature of filters that you apply. And we will see in a second that this is one of the points where we can integrate quantum computing with convolutional neural networks. Classically, the training of this network it can be done efficiently, for example, with differential methods, most notably via backpropagation. So, the most complex and successful convolutional neural networks are often also computationally intensive models. So the question that we may ask ourselves during this lecture is, of course, can quantum computing become a resource in this case? Well, to answer this question, there have been essentially three kinds of approaches. The first one is a direct approach. So in this strategy, we want to directly implement the whole convolutional neural network computation on quantum hardware, hoping, for example, for quantitative speedups. Other approaches aim instead at better performances or novel areas of application. Now, let's quickly review these three options with some examples. So the first idea that one may have, as I said, is a direct quantum implementation of convolutional neural networks on quantum hardware. The strategy here is to design and implement a quantum model which performs all the classical neural network operations directly on a quantum processor. Here I list a few examples again from the literature, but there are many more around, and again, I encourage you to go and have a look. The key features are of this kind of class of models are that, first of all, with some assumptions, provable speedups can in principle be achieved based, for example, on faster linear algebra manipulations. However, there are also some bottlenecks that one has to overcome before being able to actually achieve in practice these speedups. For example, there is the usual data loading bottleneck, which typically requires the use of a QRAM to essentially interface classical data and quantum states. Moreover, the algorithm can in general require non-trivial quantum subroutines, for example, the quantum Fourier transform or the quantum phase estimation, which are, of course, probably faster than classical counterparts, but are also not easy to implement today on real quantum hardware with many qubits. So, to open up more near-term possibilities, people have also started to think about extending the capabilities of convolutional neural networks by introducing, for example, quantum kernels or filters as a new kind of transformation that one can integrate with classical convolutional layers, for example. An example is the so-called convolutional neural networks idea that was introduced in this work. And what you do here is that you take the inputs that you would normally send to a classical filter, namely the pixel values, and you use them as parameters in a quantum feature map. You can then add some trainable components into the quantum circuit that you use and take the output of a measurement as the convolved feature that you then feed into the feedback into your convolutional neural network. A good aspect of this model is that it is in principle compatible, so directly integrable with existing classical architectures, and it does in fact target not quantitative but qualitative advantages over classical methods. For example, by assuming that if the quantum feature map that we use is hard enough to simulate classically, it may also be able to capture correlations which are not easy to analyze with classical methods. Okay, so finally, what goes by the name of quantum convolutional networks is a model like the one that I'm showing here. Now, the strategy is to build a quantum machine learning model which is only inspired by the structure of classical convolutional neural networks, but can be applied also for more general purposes. This model, as you see, is constructed with the same philosophy that you would use with classical convolutional neural networks. And you have, for example, a sort of convolutional layers in which you apply possibly translation invariant local unitaries to subset of qubits, very similarly to how you would apply the translationally invariant filters to local portions of an image. You then have pooling layers which reduce the dimensionality of your system by measuring some of the qubits and using, for example, the classical information from these measurements to control operation on the remaining ones. You alternate these convolutional and pooling layers for a few times, and then you apply the quantum equivalent of the fully connected layer, which is essentially a unitary operation on the remaining qubits after all the dimensionality reduction steps. The output is obtained as usual by measuring some observable on the quantum state that you have at the end of the computation. The key feature of the quantum convolutional neural network idea is that they can have very few parameters, and then in principle they are easier to train than full quantum neural networks. In fact, there is even a recent proof that quantum convolutional neural networks don't suffer, for example, from vanishing gradient problems, as we will see in one of the next lectures. Quantum neural networks can be used to analyze both classical data and quantum states. Now, this last idea of doing quantum machine learning directly on quantum states, so on quantum information, brings us to the next step of our exploration. So far, the idea was that we have some classical input and we would like to collect some classical output at the end, so that the model that we put in between, be it classical or quantum, is something that performs a generic transformation of classical data into classical data. Now, if we turn our attention to quantum data and quantum states, we can ask ourselves, first of all, what is the most general function or transformation that we can achieve on quantum states? And second question, is it possible to build a trainable model that is able, in general, to approximate this quantum transformation? In the quantum case, the most general transformations that you can perform are called completely positive maps. The answer to the second question is dissipative quantum neural networks. These are an example of a quantum machine learning model which is designed precisely to achieve universal quantum computation capabilities. Dissipative quantum neural networks use general quantum operations, both unitary ones and, for example, partial trace operations that are equivalent to discarding some of the qubits. And just like classical neural networks have layers composed by simple parametric nonlinear functions, the architecture here is built up in such a way that every layer is essentially a small, completely positive map. And the total output is a general composition of these transformations. The main idea is therefore the following. You start your computation with a register of qubits which contains some input quantum state, and you possibly perform some operations on them, and then you put in contact with another fresh layer initialized, for example, in some reference initial state. What you do is that you perform a controlled operation from the old to the new layer, and then discard the former. Now, I hope this reminds you of the perceptron concept that we introduced at the very beginning, so that in a sense, dissipative quantum neural networks are collection of quantum perceptrons, just like classical neural networks are collection of classical perceptrons. This is the end of this second part in which we explored different quantum models for neural networks. And now let's conclude this lecture with a somehow lighter topic. And let me show you a very simple example of how you can, in principle, build and implement a quantum feed-forward neural network for a simple classification task. This will be, as I said, a very introductory example based on a quantum model for binary artificial neurons and feed-forward neural networks that you can find in the literature. But I hope it will be useful to review some of the basic steps that one usually takes and maybe encourage you to implement it yourself in Qiskit. Okay, let's say we have the following task. We have 2x2 black and white images, like black and white pixels, and we can have, for example, diagonal images like this. We can have horizontal lines, we can have vertical lines, and we can have, for example, single dots. In general, we have 16 different patterns in these simple 2x2 images. Now, can we build, the question that I ask is the following. Can we build a model that is able to recognize among all the possible 2x2 black and white pictures, only the ones which contain either an horizontal or a vertical line? So essentially, these examples are, for example, accepted, these are fine, but these ones are not. To tackle this classification problem, the first step we have to take is, of course, to define an encoding scheme for our data. And here we will use a simple form of discrete amplitude encoding. So let's say we start with our black and white image like this. And the first step is, of course, to convert the visual information in a mathematical form. For example, we associate binary values to black and white pixels and say black pixels will be associated to value 1 and white pixel will be associated to value 0. Actually, let me do a further step now. The relevance of this will become clear in a second. And associate, in fact, -1 to black pixels and +1 to white pixels. So essentially -1 to the original binary value that we gave at the beginning. So when we do this, our 4-dimensional input is now essentially transformed into a vector of 4 binary values, which can either be plus or -1. Now, imagine we take a balanced superposition of computational basis states for n qubits. With this class of states, we can represent 2 to the n dimensional binary vectors like these ones in this superposition. And we can do so by adjusting the phases that appear in front of computational basis states. Now, the class of encoding states that we will use are the so-called real equally weighted states. Real because the coefficients are real values, in our case either +1 or -1, and real and equally weighted because they are a balanced superposition with the same probability over the whole computational basis. Now, the most important feature of this amplitude encoding scheme is that the scalar product in the quantum mechanical sense between any two encoding states, say one associated to an input vector and one to the weight vector, is directly proportional to the combination of input and weights that a classical perceptron would compute. Of course, it's not sufficient to just define how the encoding is done, but we also have to explicitly show, if we want to implement this in practice, how these states can be prepared and manipulated in a quantum circuit. So suppose, for example, that we have an input like this, which corresponds to a quantum state with 3 minus signs and 1 plus sign. Since we have 4-dimensional inputs, we will need 2 qubits to encode them. And we can start, for example, from an equal superposition of all the computational basis states. For example, we can start by preparing our qubits initialized in some reference state like 0 and apply parallel Hadamard transformation to obtain this equally weighted superposition of all computational basis states with all plus signs. Now, we can change the signs in front of each computational basis, for example, with direct sign flip operations, which can be implemented using these structures that make use of an additional qubit that we later discard. So as you see, by selecting the right operation, we can essentially manually adjust the signs that we want in the state. We will call this, as I said, the direct sign flip approach. And of course, this is far from being the optimal solution. To obtain a better strategy, we have to realize that our family of encoding states that equally weighted states are actually related to another family of quantum states, which are called quantum hypergraph states. Quantum hypergraph states are, of course, associated to the mathematical objects known as hypergraphs, which are a collection of vertices, just like regular graphs, but with a generalized set of edges which can in principle connect any number of nodes, not just the regular two as in normal graphs. For example, this is an edge that connects three vertices. To build a quantum hypergraph state corresponding to a mathematical hypergraph, what you do is that you take as many qubits as nodes in your hypergraph and you apply controlled or multi-controlled Z operations whenever you have an edge in the hypergraph. Now, it's easy to see that the class of real equally weighted states that we are using for our encoding is exactly coincident with the class of hypergraph states. So the algorithm that is known from the literature for the generation and manipulation of hypergraph states can also be used for our purposes. This leads us to the optimal preparation and manipulation procedure for our encoding states, which uses a smaller number of multi-controlled operations compared to the direct sign flip approach. So here is how, for example, the same state preparation routine that we analyzed before would look like if we used the hypergraph state preparation algorithm. So the starting point is again 2 qubits prepared in a balanced superposition of all the computational basis states, but then we just apply a single qubit Z rotation on the first qubit and on the second qubit, plus a single controlled Z, which is needed to adjust the last sign. Now, as you can easily see, the advantage of using the hypergraph state routines is that it reduces the number of controlled operations that we have to perform by leveraging the correlations between the signs that are introduced by single and few qubit operations. Of course, these routines can also be generalized to any arbitrary dimension. Okay, so we can now move to the next step and design the elementary unit of our classifier, namely a quantum artificial neuron. The basic model that we mimic is still the original one that we discussed at the beginning, the classical perceptron model introduced, for example, by McCulloch, Pitts, and Rosenblatt. But we want to run it on a quantum processor. A possible way of doing this is a sequence of 2 unitary operations plus a measurement, as I'm showing in this diagram. So imagine you start with a register of encoding qubits that are all initially prepared in the 0 state. With a first unitary UI, we can prepare a quantum state representing the input that we want to analyze. So this will be one of the state preparation routines that we described before. In the second step, we introduce the information about the weights that we want to associate to this perceptron by a second unitary transformation UW, like this one, which is subject to the following constraint. So UW is one unitary operation that, if applied to the quantum state corresponding to the encoding of the weight that we want, it will give us an output all qubits in state 1. Now, thanks to these simple constraints, it's not difficult to see that at this stage of the computation, the state of the encoding register has a coefficient associated to the last computational states, namely the one where all qubits are in state 1, which is in fact the overlap between the input and the weight encoding states. Remember that this is related to the combination of input and weights that the perceptron computes. In order to determine the activation state of the neuron, we simply write this information onto an additional qubit initially prepared in the 0 state with a multi-controlled NOT operation. We can then measure the activation state of the neuron by measuring the output qubit. Now, if this output qubit is found in state 1, which happens with a probability which is proportional to the modulo square of this combination of input and weights, then we say that the neuron is in the active state. On the contrary, we say that the neuron is in a rest state if the measurement gives an outcome 0. What happens, for example, with our 2x2 black and white images with a single artificial neurons of this kind? if the input is, for example, this image with a vertical line, and the weight is identical to it, then the perceptron will always be active. So the activation probability is equal to 1. Actually, due to a global phase invariance embedded in our encoding scheme, the same is also true if input and weight are negative images of each other. All other combinations either give a 0 activation probability when input and weight are perfectly orthogonal, or a very small activation well below 0.5, like in this case. Now, this model was actually implemented on real IBM quantum processors, and this is, for example, the activation pattern that you can recover from a 5-qubit device using the hypergraph states routine for preparation and manipulation of the states. You see that, of course, despite some hardware noise, the actual activation pattern of the neuron is computed perfectly, and all the classification tasks are carried out perfectly. In particular, with respect to this last point, we noticed that since the activation probabilities peak in the diagonal and anti-diagonal of this plot, the meaning is that a single neuron implemented in this way can detect inputs which are identical or the negative of the given weight vector. However, single nodes are not enough to perform the task that we originally wanted to do. So to simultaneously identify vertical and horizontal lines and single them out from all the rest. Now, to finish the construction of our classifier, we have to build a small network which extends the capabilities of the single nodes. Now, a possible solution of this simple task is this 3-node network that I'm showing here. So as you see, there are 2 neurons in the first layer, which recognize either vertical or horizontal lines, plus a third one, which receives a signal from the first 2 and decides whether any of the 2 was active. So the ideal activation pattern of the network is the one that you see here on the right, and you see that the network is active with probability 1 precisely only on those inputs that contain a vertical or a horizontal line. In all other cases, the activation probability is either 0 or below 0.5. Okay, so how do we build this network in practice on a quantum register? Well, the construction is again very simple, and we just reuse the general structures that we introduced for individual artificial neurons, for the one with UI and UW, and we repeat this in parallel for the 2 neurons which are present in the first layer. Of course, here the W operation will be parameterized differently to recognize, for example, vertical and horizontal lines. Now, what you have to do is to connect these neurons to the output layer, so transfer the activation information to the last neuron, which in our case can be implemented with just a single qubit. Now, if you recall how quantum perceptrons work, namely that they are essentially control unitary operations, it will not come as a surprise that this transfer of information can be done with control Z operations, for example. So for the third neuron, the input preparation stage is replaced by these controlled operations, and we only have to apply the final UW3, which analyzes the state, and essentially then we have just to measure the final, this output neuron, to determine the activation state of the whole network. Now, in this simple case, we could actually cheat a bit and forward the information even by just using intermediate measurements in the first layer, and then controlling classically the preparation of the state in the last neuron. Okay, this is what happens if you run this experiment on real quantum hardware. And actually on the left, we have a simplified experiment where we used this classical feed-forward of information. While on the right, we have the more interesting case in which the whole network is operated coherently, and this requires 7 simultaneously active qubits for this simple example. Again, as you see, even though there are some quantitative errors due to the noise on the devices, in both cases, the classification is carried out perfectly. So the network does, in fact, recognize only and all the states that we wanted at the beginning. Okay, so this is the end of this lecture. I hope you enjoyed it, and I thank you very much for your attention. I hope to see you again for the next lecture, and thank you very much and have a nice day.